Okay. No worries. No, so we already started with the discussion based on your response.
Okay.
About the definition, what is now geometrical interlocking. Yeah, and
so what's your thought?
Well, to me, it's just a term. If you have two fitting geometries and you start to move them, they're interlocking, therefore they cannot move and they have to dilate in order to so for me, that's the conceptual definition of what geometrical interlocking was to me, yeah? So...
Yes, but my concern was on the first series of tests where you limit the vertical displacement.
Mm-hmm.
Right? I think that you won't have any dilation in that case, right? So you're shearing through the material directly.
You have to.
Yeah, so I think that cannot be counted as interlocking. That was my concern. So I was thinking, you should not limit the displacement, but you can actually apply different levels of pressure. So if the pressure is high, then you won't, have a lot. So that's the latency suppression, right?
The fixed,
so
the zero displacement means infinite confining pressure.
Yes.
Right?
Yeah, exactly. And but it depends on the strength, right, of the socket itself. Yeah.
So I think we just discussed, you and I, that okay, instead of, so you can then add one more factor, which is the confining stress, by using that servo control which you just mentioned, see, right?
Yes.
Yeah.
As a case 6, additional case 6.
As case 6, yes. So you have five variables. One is the cohesion at the interface, one is the friction at the interface. Then you have the integrity of the mineral quality, the CC bond strength / holes in your crystal, right? That was, I'm not sure if there's one or, that's 2 variables, right? So then we're at 4. What else did you have? Number 5?
Dilatancy. It restricts the constraint of vertical displacement.
Okay.
Free movement on the vertical.
So instead of free and 0, you can have 2 intermediate values of 100 and 200 kPa. Is that possible? Then so you can have fully free dilation, means there's no stress at the top, and you start shearing, so they roll out of position once they break the GC bond. But if you have some confining pressure, and you say there is a possibility to apply some confining pressure, right? So to just move the 2 host drains until they have a concrete force.
Just keep a constant force there, right? Like, I think that's typical, right? That's the servo control method in PFC.
Yeah, in all the DEM, you don't just apply the force directly. Instead, you control the displacement of the ball. So until it reaches to based on the stiffness and overlap.
Okay.
Yeah. But so in your email, I noticed that you want to define the dilatancy by that dy over dx. So you're using that ratio as to quantify the effect of dilatancy, right? I guess yes. And you propose that in all these sub cases, we should always apply this confining pressure, maybe 100 kPa, 200 kPa, and then redo all this all the simulations just by keeping the constant confining pressure. And is that what
was my thought? Yeah, that was my thought. Yeah.
And you want to
because if you fix it, then there's no geometric effect, right? So you are shearing through the socket itself. So the strength of the socket actually controls the strength.
Well, if you would have very strong CC bond and very low GC bond, then you would break all the GC bonds and then you can tilt. Then the entire...
But you're limiting it, right? You're limiting the vertical.
No, so in this case you have 0 vertical, right? The current scenario is either free vertical or 0 vertical.
Okay.
So 0 is high confining pressure at the range, and if you then start shearing, only when it's the GC bond breaking and overcoming the friction at the GC bond level, if that happens, then the wedge would
rotates.
The socket would tilt.
Tilt.
Rotate.
Yes, tilt.
So both particles will also tilt.
Yes.
Or the bottom?
Not.
The-
Particles are moving horizontally, but as they move, the wedge can rotate.
Oh. How do you show the interlocking effect then? How do you? I
Yes,
mean,
that was what I was just discussing. So with spherical shaped particles with spherical shaped convex wedges, or is it concave? Hollow. With the same hollow wedges, you cannot say there's interlocking because they can easily rotate within the socket. So I guess real geometrical interlocking would be if this is not a perfect sphere. Then it cannot rotate out of position anymore either. But okay, this is not possible in maybe, but complex PFC if you have to have non-round particles and non-perfectly spherical particles. But in reality, grains are not purely spherical. So if you would have a wedge which is not purely spherical as well, you want to shear it, it cannot rotate out of position because you get peak force at some point in this socket.
okay, so now it's the balls are now moving vertically, but the socket may rotate.
The socket may rotate, and therefore you have no interlocking, unless you assume that the GC bond is not only cohesive but also frictional, and the frictional force along the GC contact is representing the surface roughness of that grain interface.
Yeah, I guess that also makes sense. But my thinking was, first we already have a framework to quantify that. So it's just an analogy to the direct shear. Second is in the realistic. So now you have these two particles, but in reality, these two particles are inside a sample, right?
Yeah.
And then these samples will have those, confinement or,
Yeah, multiple directions.
kinematic, yeah. So, in what scenario is they are both fixed? I mean, vertically.
True. So realistically,
Right.
they're not perfectly fixed because the force on those two particles is never perfectly horizontal.
Move horizontal.
And as soon as they
So
move,
if you can figure, so my point is, okay, if you can figure a way to make an equivalent quantification of that, interlocking effect of those fixed one, I'm okay with it. Right. So
can you get as you shear, right? As you shear in these grains, and assume zero cohesion of the GC bond, just frictional surface. As you shear, can you get a resultant force then in the vertical
Yes.
component?
Yes. I can measure that. I can monitor that.
You can measure the vertical force.
Yes. I can monitor that.
So either you plot the vertical force as a function of horizontal displacement.
That's what I'm gonna do in the dilation case, in the free dilation case.
Oh, that's a free dilation case.
Yes.
No,
And-
in free dilation case, you're allowed to move freely, right?
There's a figure that will be a y displacement as a function of the horizontal displacement at a different friction coefficients. That's why you say if you have because this energy will dissipate through the friction, right, based on the Taylor's theory. That's why I propose if you have a smooth or a very smooth interface, and then you gradually increase the surface roughness by changing the friction ratio, the coefficients, and then I assume that this y displacement will change accordingly. That's why I put that in the free dilation case. But
Okay.
yes, but if you want to quantify that, I can also do that by applying. But then there will be an additional story, because there will always be like a 100 kPa constant confining pressure. In that case, I can also monitor the force, and then associated displacement, plot dy over dx and then plug all these numbers into the Taylor's equation. And I think because you already know the friction coefficient, the mu value, right? And I can also calculate the peak shear strength accordingly. Just in case it will reach to the peak shear strength. If you have a very strong bond, I don't think it may never shear. Or if you rotate it, if you just tilt to one side, it will never shear. So in this case, your tau will be 0. Yeah. And the sigma n prime, this value we also know because this is predefined. So in this way, you can quantify this so-called interlocking effect.
Okay.
You don't quantify this interlocking effect because based on that Soga and Michel's textbook, you call this to quantify the dilatancy. But to quantify the interlock.
What's the reason of dilatancy?
Well, intuitively, it's just you have a very strong CC bond.
The dilatancy is caused by that interlocking. Right? So this theory is called the interlocking dilatancy theory. So they are the same thing.
Yeah.
So I've shared 2 papers with you.
Yeah, sure. Please do so.
Got it.
Yeah.
One is Rowe, one is Taylor.
Nice. Yeah, please share. Interesting. This is a bit beyond my comfort zone.
So doctor, I just want to make sure we're on the same page. So what do you propose to modify because I will resimulate all these things. What is your?
So I have 2 options, right? Suggestions. I don't run these tests, but I think so you know the details. So either you just build on what you already have, just change the narrative a little bit, right? So you emphasized on geometric interlocking in the title. So I thought, you need to be very clear about what you are showing. I think what you did is actually just strings in general, right? So including not only interlocking, but also, for those restricted ones especially, right? So I think that's mainly due to, right? So that's not geometrical interlocking to me. But you may argue, right? So that's a debate. So that's one way to do it. You can just focus on the existing data, but build a story around it. But if you really want to show the geometric interlocking effect, I prefer to just quantify it using the existing framework.
Okay.
Right. So I think the easiest way is just to have these two balls, and you apply. For example, you have a control case, right, with a particular shape or the strings or morphology, whatever you set up. So in this control case, you can vary the confinement pressure, right? And then you do a series of this.
Okay.
You measure dy, dx.
Okay.
Now this is very similar to direct shear test, right?
Yes.
So
yes.
now you can have a PQ curve, and then you also have epsilon A. In this case, it's dx basically, right? So from that chart, that slope is actually the dilatancy. It's very, straightforward to quantify.
Okay.
And then next step is if you want to show the effects of all those things like the bond strings or the friction or collision at the interface or inside those cementation particles, right? Then you can just do another test, a series of tests for each of that factor. You can actually do the direct shear test.
But all this
that means a lot of tests.
That's doable, but I just want to make sure all those following tests will on the basis that I always apply a constant confining pressure. Is that what you propose? Or
I think the best way is a series of constant pressures.
Yeah, but I would say that would be a lot of tests. Is it not enough to just show the effect of confining pressure to make the case for actual interlocking? So you take the control case and then you just vary, and now you did 0, you did infinite, you take 1 or 2 stress levels in between, and then do the same shear test, and then you can show that effect of confining pressure, and then plot only for those cases the dy dx curves.
Yeah. Yeah, that's okay.
So that means.
So if you only one level, if you only have one level like 200 kilopascal confinement pressure, you can still show the
Trend.
effect on the latency.
Okay.
Right?
Okay.
Or maybe 10,
Yeah,
20,
yeah.
50, 100.
Yes,
but
yes.
On the other hand, I don't know what the actual values at the grain stress are. Huh? Those are
Yeah,
higher
maybe you
than
just use force divided by that.
yeah.
Area.
But
Okay.
then, one other question I have, because so we can only show so the dx dy only happens, right, if it would be a frictionless contact on the socket, friction and cohesionless socket, it just rotates out of position. There will be no dy. dy dx is 0. So then I just wonder, is it because of the shape and just the limitation that we're just sharing two round particles perfectly horizontal that we do not get it? Because otherwise we can only get it well, you did a simulation with free movement, right?
Yes.
And then it doesn't rotate, or does it?
It actually moves out of the socket.
It moves out of the socket.
Yes.
But this is in the case when you have no cohesion and just friction, or you have a little bit of cohesion and a little bit of friction.
No cohesion. If you have a cohesion, it will kind of like drag the upper host grain.
Yes, and if you have no cohesion, just friction, then it rotates out of position, and the upper ball goes out of position.
Yeah.
It's not that then, well, because you have at one point it just sticks to the friction. It would be very coincidental if the friction on both sides would be exactly the same. So it means that as soon as the friction is overcome, and probably in the top grain, then the upper ball shears out.
It will keep going out because due to the inertia. Because in this case, if you don't give a damping ratio to dissipate the energy, it will just keep going up because there's no gravity in my case.
No. Oh yeah. So you move up, and at once it has a vertical.
Yes, always go all the way up.
Yeah, I'm just wondering whether the dy really says something, right? Because if the CC bond of the crystal is very strong internal, the grain will always move out. But then the amount of displacement is just a factor of the size of the wedge, right? Because it has to just get out of the wedge. I wonder if it has anything to do with the actual dilatancy then. I mean, if you would make the wedge a little bit longer, then it has to move fully out of the wedge.
So it's effect of the dimension of the wedge is another case.
Correct. If you have like a very small part of the circle at small dilatancy,
Yes.
you get out of your wedge. And if you have like a full half circle, then it's
I see.
And it can only so if your wedge is more than covering half of the sphere, you cannot.
I think that's the meaning of that dilatancy. If you have a fixed shape and fixed friction between the particle and that socket, the dilatancy will be a constant at a particular confinement, right? But if you have different confinement, so if you increase the confinement, the dilatancy actually can be surprised.
I don't think it will change it. It's just a function of wedge size, right?
If your confinement is very high, it will have a tendency to go through that socket.
Yeah, then it will break the socket faster, or a part of the socket, the edge of the socket, right?
Yeah. So.
Yeah. So I think it's valuable to add some confining stress levels to see.
Yes.
So if you vary the confining stress, then you start breaking the socket faster.
Okay. In the case 6, additional one, I will quantify that dy dx to show this dilatancy, to calculate that corresponding dilatancy value with a different confining pressure from 50, 100.
It's exactly the same for each confining pressure until you start breaking the socket.
Yes, because I don't know what is the threshold value will be. So I'll do in that case, I will do another set of parametric analysis. So Dr. Tao, is that okay with you?
Yeah.
Yeah, only
Okay.
if you can justify the first series,
Okay.
right? How do you demonstrate the interlocking there? I don't know. To me, interlocking is just
Okay.
No,
I see your point. Okay.
yeah.
To me,
So
breaking
just build around it if you can justify it or explain it.
it isn't. I mean, if you break the socket, this is interlocking, right? Breaking you don't have zero the latency, but you only start breaking. Well, it's a function of internal strength of the socket, and strength of the GC contact.
To me, it's more like a cementation effect, or more like a apparent cohesion. Yeah, but maybe I don't know. Yeah,
No, I mean
that's my 2 cents.
Yeah, okay. Because I think every time, so if you just have a certain shape of socket, as long as the confining stress is low enough that it doesn't break the socket, you always have the same
The
D1.
dilatancy will be the same. Yeah. So you mentioned that you changed the morphology. I thought you changed the socket. You are in your I forgot the number 1 or number 2
Number
case.
1.
You mentioned that you changed the morphology.
Yeah.
That morphology is the cementation particles? Or?
Calcite morphology. No, calcium carbonate morphology with the calcite, vaterite, or aragonite. They correspond with different CC bonds.
Integrity.
Integrity.
It's like a T or the CC bond strength.
So
Yes.
it's not the shape of the socket?
No.
Okay.
But that's another variable, shape of the socket.
No.
Well, you
Don't
have
do
two,
that.
you have the full cover, you have the full cover, and you have the socket size. Yeah. All right. Yeah, I do understand your thing now, Julian.
Maybe I'm too locked in the
You do have to
definition
talk.
of that. Right, so I teach that course and I explain it like that. So,
Yeah.
but yeah, I'll share some readings to you guys. And
Thanks.
if you, as I mentioned, if you can build a story around it and make sure that the interlocking effect is sufficient demonstrated and defined, yeah, I think it's fine.
Okay.
Yeah.
Also,
Yeah.
so you say the geometrical interlocking, this term is not really appropriate under this context?
Yeah, exactly. At the grain
Yeah,
level.
to me, for the
Oh.
first series of tests where you fix that, I feel
I see.
it's contradictory to the conventionally defined interlocking.
Oh, okay.
Yeah, but
I feel that's my
conventional definition is not at particle scale, right?
yeah.
It's at element scale, and then I do see the point. If you have grains with multiple contacts, and at each contact you have a wedge, then all directions are sort of constrained, right? By all, and then you start sharing that continuum with a lot of wedges, and not all wedges are in the same direction. So then indeed you are constrained in multiple directions. You have to dilate in one, and then you get dilation at the element level.
Yeah.
But that's another good question. Is the same concept of geometric interlocking a valid concept at the particle level? And I do see the point. If you have like a non-symmetrical spherical grain with a perfectly fitting socket, then you cannot then you already constrain the rotation because it cannot rotate out of its socket. But if you have a perfectly spherical ball socket, yeah, then it can rotate. Rotation is still free as soon as you break the bond, the GC bond, right?
is still, so the socket is like you are introducing additional particles to the system, and it has a different shape, and that shape provides these kinematic constraints or the movement, right? So it blocks the movement. It makes the movement of those particles less free, right? So if it's always free, then there's no interlocking. Now you are preventing it to move as it wants to, right? So that is the interlocking, right?
Yeah.
But if you break through that, maybe, I don't know. It's just, I have a thought on that. Yeah, so you can work on that, and I will read your explanation, right? So if it's convinced me, I think it's fine.
Yeah, it's philosophical, right? This discussion about the nature of interlocking.
I think that's very good discussion.
Yeah.
Right. So this is one of the first concept actually.
Yeah. I thought it was about the nature of cohesion, but we're actually also debating the nature of interlocking now.
Yeah, the cohesion is actually related to this. So originally people do that, direct shear and got that envelope, right? So the Moore Coulomb, and it found that, but clearly they're testing sand. What's that cohesion? That cohesion is interlocking.
Yes, it's at low stress shearing, right? So at the low normal stress, you get a apparent cohesion, but in fact it's just interlocking the latency, right?
Yeah.
Because you're at low stress levels.
Yeah. So that's not actually, although if you use Moore Coulomb, you get that intersect, but that is not true cohesion, right? So for that, Taylor attributes that to interlocking and used the dilatancy to explain it. I think that was the history about it.
Nice.
Yeah, so I really think within this whole discussion and paper is really fundamental theoretical, right? If we are able to bring it to the level, it's definitely geotechnique, right? Because we're really discussing the fundamentals by Terzaghi, Schofield, Rowe, Taylor, right?
Yeah.
The whole definition part. So how do biocemented sands work? If we see that from all the SEM images, the crystals are really detached from the actual host grains. If you allow them to take them out one by one.
Yeah, I think Ziwei, you already have a lot of data.
Yeah.
So you just now, I think we have different views. I think that's totally fine. And also, you just take my comments as a reviewer's comment.
Yes.
And you can actually write that part to answer my concern, right? So if I'm satisfied, so I think other reviewers may not have the similar question, right?
Yes.
So,
yes.
I think these discussions are very helpful.
Very constructive. Very constructive.
And healthy.
Yeah.
Can we write this as part of the paper, the discussion form, exactly this conversation, right? So
at the beginning.
Well, yeah, either at the beginning or the discussion.
Or in the discussion, yeah.
What,
so what was the true? What was? Yeah.
What are we actually looking at? Is this now interlocking, or is this cohesion, or is it friction? What is it? And then we can write it in the question form, and then try to discuss it in that way.
I think that's a good idea. Yeah.
Okay.
We'll just
Okay.
That's it.
time now. Oh, I have to go.
Okay.
Thanks, Julian. It was nice to have this fundamental discussion.
Okay.
Are you going on holiday now?
Yeah, we are going to Orlando. The Disney World, I think.
Nice.
Yeah.
All right. Enjoy.
4 days.
And then back again?
Yeah, then back again.
Okay.
And we will stay here around, the New Year and Christmas. So how about you guys? You have plan?
Just in New Year's, we rented the cottage, but it's like 2 hours from here.
Yeah. I'll wrap up the other 2 papers. I still have 2 more papers.
Yeah.
Okay.
Yeah.
Okay.
So
Well,
yeah, Ziwei doesn't celebrate, Christmas or New Year.
Well, celebrate with a nice fundamental discussion about interlocking.
Yeah.
I mean, it's still an interesting.
Okay.
Yeah.
Oh, doctor, so just in case, just for that, if you, in case you are not in here, and if you're for the next week, maybe we got that proofreading link of that previous ACTA paper. So if you're okay with that, can me and Dr. Van Passen, we just do the proofreading, if you agree?
Yeah, sure.
Okay.
For
Just
that
one-
one, yeah.
okay.
If it
Previous
comes in,
one, I think it's already done, right?
Yeah.
Yeah, they didn't send proofreadings, so it is accepted. But then they asked me which version they should look into to do the proofreading. But then I never heard back from them afterwards.
Oh, yeah. I think they maybe have too many papers now for
Yeah.
that.